Hello. So today I will complete the course about essential cloud infrastructure, the foundation. I will conclude it with a lab about compute engine, and then maybe we will continue with other contents from other courses. Therefore, let's go. Let's start and let's put our hands on practice stuff.
Now that you have completed the lab, let's dive deeper into the compute options that are available to you in GCP by focusing on CPU and memory. You have three options for creating and configuring a VM. You can use the GCP console, as you did in the previous lab, the Cloud Shell command line, or the RESTful API. If you'd like to automate and process very complex configurations, you might want to programmatically configure these through the RESTful API by defining all the different options for your environment. If you plan on using the command line or RESTful API, I recommend that you first configure the instance through the GCP console, and then ask Compute Engine for the equivalent REST request or command line, as I showed you in my demo earlier. This way, you avoid any typos and get drop-down lists of all the available CPU and memory options. Speaking of CPU and memory options, let's look at all the different machine types that are currently available.
When you create a VM, you select a machine type from a machine family that determines the resources available to that VM. There are several machine families you can choose from, and each machine family is further organized into machine series and predefined machine types within each series. A machine family is a curated set of processor and hardware configurations optimized for specific workloads. When you create a VM instance, you choose a predefined or custom machine type from your preferred machine family. Alternatively, you can create custom machine types. These let you specify the number of virtual CPUs and the amount of memory for your instance. There are 4 compute engine machine families: general purpose, compute optimized, memory optimized, and accelerator optimized. Let's look at each in more detail. The general purpose machine family has the best price performance with the most flexible virtual CPU to memory ratios, and provides features that target most standard and cloud native workloads. The E2 machine series is suited for day-to-day computing at a lower cost, especially when there is no application dependencies on specific CPU architecture. E2 VMs provide a variety of compute resources for the lowest price on Compute Engine, especially when paired with committed use discounts. You simply pick the amount of virtual CPU and memory you want, and Google provisions it for you. The standard E2 VMs have between 2 and 32 virtual CPUs, with a ratio of 0.5 GB to 8 GB of memory per virtual CPU. They are a great choice for web servers, small to medium databases, development and test environments, and many applications that don't have strict performance requirements. They offer a compatible performance baseline with the current N1 VMs for those of you who have been using them. The E2 machine series also contains shared core machine types that use context switching to share a physical core between virtual CPUs for multitasking. Different shared core machine types sustain different amounts of time on a physical core. In general, shared core machine types can be more cost-effective for running small, non-resource intensive applications than standard high memory or high CPU machine types. Shared core E2 machine types have between 0.25 and 1 virtual CPUs with 0.5 GB to 8 GB of memory. The N2 and N2D are the next generation following the N1 VMs, offering a significant performance jump. N2 and N2D are the most flexible VM types and provide a balance between the price and performance across a wide range of VM shapes, including enterprise applications, medium to large databases, and many web and app serving workloads. Committed use and sustained use discounts are supported. N2 VMs support the latest second-generation scalable processor from Intel with up to 128 virtual CPUs and 0.5 to 8 GB of memory per virtual CPU. Cascade Lake is the default processor for machine types with up to 80 virtual CPUs. For larger machine types, Ice Lake is the default processor for specific regions and zones. N2D are AMD-based general-purpose VMs. They leverage the latest EPYC Milan and EPYC Rome processors and provide up to 224 virtual CPUs per node.
Tau T2D and Tau T2A VMs are optimized for cost-effective performance of demanding scale-out workloads. T2D VMs are built on the latest 3rd-gen AMD EPYC CTM processors and offer full x86 compatibility. They are suited to scale-out workloads including web servers, containerized microservices, media transcoding, and large-scale Java applications. T2D VMs come in predefined VM shapes, with up to 60 vCPUs per VM and 4 GB of memory per vCPU. Tau T2A machine series is the first machine series in Google Cloud to run on ARM processors. The Tau T2A machine series runs on a 64-core Ampere Ultra processor with an ARM instruction set and an all-core frequency of 3 GHz. If you have containerized workloads, Tau VMs are supported by Google Kubernetes Engine to help optimize price performance. You can add T2D nodes to your GKE clusters by specifying the T2D machine type in your GKE node pools.
The compute optimized machine family has the highest performance per core on Compute Engine and is optimized for compute-intensive workloads. C2 VMs are the best fit VM type for compute-intensive workloads, including AAA gaming, electronic design automation, and high-performance compute.
Specifying the T2D machine type in your GKE node pools.
The compute optimized machine
Highest performance per core on compute engine.
family has the highest performance per core on Compute Engine and is optimized for compute-intensive workloads.
He said the highest performance per core.
Series is suited for day-to-day flexible virtual CPU to memory ratios. This machine family has the best price performance with the
Price performance. The
most flexible virtual CPU to memory ratios and provides
price performance. Best price performance ratio.
the compute optimized machine family has the highest performance per core on Compute Engine and is optimized for compute intensive.
Highest performance per core. Highest performance per euro, high performance per
Optimized
core.
machine family has the highest performance per core on Compute Engine and is optimized for compute-intensive workloads. C2 VMs are the best fit VM type for compute-intensive workloads, including AAA gaming, electronic design automation, and high-performance computing across simulations, genomic analysis, or media transcoding. They might also be
Ultra performance for compute-intensive workloads, compute-bound workloads, high performance web serving, gaming, ad serving, performance computing, media transcoding, AI/ML. Instead, here we have back office app, web serving, app serving, small billion databases, web serving, app serving, back office apps, microservices, cache, media streaming. Okay, scale out applications. So general purpose are just for generic applications. Instead, here we have compute optimized machine for media transcoding, high performance computing, AI and ML, gaming, high performance web serving, compute bound workloads.
machine type offer up to 3.8 GHz sustained all-core turbo and provide full transparency into the architecture of the underlying server platforms, enabling advanced performance tuning. The C2 series comes in different machine types ranging from 4 to 60 virtual CPUs and offers up to 240 GB of memory. You can also attach up to 3 TB of local storage to these VMs for applications that require higher storage performance. The C2D machine type series provides the largest VM sizes and are best suited for high performance computing. The C2D series also has the largest available last level cache per core. The C2D machine
electronic design automation.
series comes in different machine types ranging from 2 to 112 virtual CPUs and offers 4 GB of memory per CPU core. You can also attach up to 3 TB of local storage to these machine types for applications that require higher storage performance. C2D VMs are available on the 3rd generation AMD EPYC Milan platform.
The H3 series offer 88 cores and 352 gigabytes of DDR5 memory and are available on the Intel Sapphire Rapids CPU platform and Google's custom Intel Infrastructure Processing Unit (IPU).
The memory optimized machine family provides the most amount of compute and memory resources of any Compute Engine family offering. They are ideal for workloads that require higher memory to virtual CPU ratios than the high memory machine types in the general purpose machine family. The M1 machine series has up to 4 TB of memory, while the M2 machine series has up to 12 TB of memory. These machine series are well suited for large in-memory databases like SAP HANA, as well as in-memory data analytics workloads. Both the M1 and M2 machine series offer the lowest cost per HANA, while the high memory machine types in the general. They are ideal for workloads that require higher memory to virtual CPU ratios than the high memory machine types in the general purpose machine family. Family provides the most amount of compute and memory resources of any Compute Engine family offering. They are ideal for workloads that require higher memory to virtual CPU ratios than the high memory machine types in the general purpose machine family. The M1 machine series has up to 4 TB of memory, while the M2 machine series has up to 12 TB of memory. These machine series are well suited for large in-memory databases like SAP HANA, as well as in-memory data analytics workloads. Both the M1 and M2 machine series offer the lowest cost per gigabyte of memory on Compute Engine.
Lowest cost per gigabyte of memory on Compute Engine. So here we have lowest cost per gigabyte.
Making them a great choice for workloads that utilize higher memory configurations with low compute resource requirements. Additionally, they offer up to 30% sustained use discounts and are also eligible for committed use discounts, bringing additional savings of greater than 60% for 3-year commitments.
M3 VMs offer up to 128 vCPUs with up to 30.5 gigabytes of memory per vCPU and are available on the Intel Ice Lake CPU platform. These machines are well suited for memory-intensive applications such as genomic modeling and electronic design automation and high-performance computing.
The accelerator optimized machine family is ideal for massively parallel compute unified device architecture or CUDA compute workloads, such as machine learning and high performance. Is ideal for massive
design automation and high perform. These machines
So here we have example of use cases. So huge databases. Warehousing, genomics analysis, SQL analysis services, OLAP and all TSAP workloads.
are well suited for memory-intensive applications, such as genomic modeling and electronic design automation and high-performance computing.
The accelerator optimized machine family is ideal for massively parallel compute unified device architecture or The accelerator optimized machine family is ideal for massively parallel compute unified device architecture or CUDA compute workloads, such as machine learning and high performance computing. This family is the optimal choice for workloads that require GPUs. The A2 series has between 12 and 96 virtual CPUs and up to 1,360 gigabytes of memory. Each A2 machine has a fixed number, up to 16, of NVIDIA's Ampere A100 GPUs. An A100 GPU provides 40 gigabytes of GPU memory, ideal for large language models, databases, and high performance computing.
G2 VMs offer 4 to 96 vCPUs, up to 432 gigabytes of memory, and are available on the Intel Cascade Lake CPU platform. These machines are well suited for CUDA-enabled ML training and inference, video transcoding, remote visualization workstation.
Additional information, including the latest specs for currently available machine types, can be found in the machine types documentation.
If none of the predefined machine types match your needs, you can independently specify the number of vCPUs and the amount of memory for your instance. Custom machine types are ideal for the following scenarios: when you have workloads that are not a good fit for the predefined machine types that are available to you, or when you have workloads that require more processing power or more memory, but don't need all of the upgrades that are provided by the next larger predefined machine type. It costs slightly more to use a custom machine type than an equivalent predefined machine type, and there are still some limitations in the amount of memory and vCPUs you can select. Only machine types with one vCPU or an even number of vCPUs can be created. Memory must be between 1 GB and 8 GB per vCPU. The total memory of the instance must be a multiple of 256 megabytes. Selected custom machine types can allow up to 8 gigabytes of memory per vCPU. However, this might not be enough memory for your workload. At an additional cost, you can get more memory per vCPU beyond the 8 gigabytes limit. This is referred to as extended memory, and you can learn more about this in the link provided in the module PDF, located in course resources.
The first thing you want to consider when choosing a region and zone is the geographical location in which you want to run your resources. This map shows the current and planned GCP regions and the number of zones. For up-to-date information on the available regions and zones, see the documentation linked for this video. Each zone supports a combination of Ivy Bridge, Sandy Bridge, Haskell-Broadwell, and Skylake platforms. When you create an instance in the zone, your instance will use the default processor supported in that zone. For example, if you create an instance in the US Central 1A zone, your instance will use the Sandy Bridge processor.
Okay.
Google Cloud offers a variety of different options to keep the prices low for compute engine resources. All vCPUs, GPUs, and gigabytes of memory are charged a minimum of 1 minute. For example, if you run your virtual machine for 30 seconds, you will be billed for 1 minute of usage. After 1 minute, instances are charged in 1 second increments. Compute Engine uses a resource-based pricing model where each vCPU and each gigabyte of memory on Compute Engine is billed separately rather than as a part of a single machine type. You still create instances using predefined machine types, but your bill reports them as individual vCPUs and memory used. There are several discounts available, but the discount types cannot be combined. Resource-based pricing allows Compute Engine to apply sustained use discounts to all of your predefined machine types usage in a region collectively rather than to individual machine types. If your workload is stable and predictable, you can purchase a specific amount of vCPU and memory for a discount off of normal prices in return for committing to a usage term of 1 year or 3 years. The discount is up to 57% for most machine types or custom machine. The discount is up to 70% for memory-optimized machine types. Preemptible and spot VMs are instances that you can create and run at a much lower price than normal instances. For both types of VM, Compute Engine might terminate or preempt these instances if it requires to access those resources for other tasks. Both preemptible VMs and spot VMs are access Compute Engine capacity, so their availability varies with usage. Importantly, preemptible VMs can only run for up to 24 hours at a time, but spot VMs do not have a maximum runtime. The ability to customize the amount of memory and CPU through custom machine types allows further pricing customization. Speaking of sizing your machine, Compute Engine provides VM sizing recommendations to help you optimize the resource use for your virtual machine instances. When you create a new instance, recommendations for the new instance will appear 24 hours after the instance has been created. Compute Engine also has free usage limits.
Sustained use discounts are automatic discounts that you get for running specific Compute Engine resources, vCPUs, memory, and GPU devices, for a significant portion of the billing month. For example, when you run one of these resources for more than 25% of a month, Compute Engine automatically gives you a discount for every incremental minute you use for that instance. The discount increases with usage, and you can get up to 30% net discount for instances that run the entire month. This table, shown on this slide, describes the discount you get at each usage level of a VM instance. To take advantage of the full 30% discount, create your VM instances on the first day of the month because discounts reset at the beginning of each month. The graph on this slide demonstrates how your effective discount increases with use. For example, if you use a virtual machine for 50% of the month, you get an effective discount of 10%. If you use it for 75% of the month, you get an effective discount of 20%. And if you use it for 100% of the month, you get an effective discount of 30%. You can also use the GCP pricing calculator to estimate your sustained use discount for any arbitrary workload. Compute Engine calculates sustained use discounts based on vCPU and memory usage across each region and separately for each of the following categories: predefined machine types and custom machine types. Let's go through an example where you have two instances that are in the same region but have different machine types and run at different times of the month. Compute Engine breaks down the number of vCPUs and amount of memory used across all instances that use predefined machine types and combines the resources to qualify for the largest sustained usage discounts possible. As shown on the slide, you run the following 2 instances in the US Central 1 region during a month. For the first half of the month, you run an N1 Standard 4 instance with 4 virtual CPUs and 15 GB of memory. For the second half of the month, you run a larger N1 Standard 16 instance with 16 virtual CPUs and 60 GB of memory. In this scenario, Compute Engine reorganizes these machine types into individual vCPUs and memory resources and combines their usage to create the following resources, as shown on the bottom. 4 virtual CPUs and 15 GB of memory for a full month, and then 12 virtual CPUs and 45 GB of memory.
As I mentioned earlier, a preemptible VM is an instance that you can create and run at a much lower cost than normal instances. See whether you can make your application function completely on preemptible VMs, because a 60 to 91% discount is a significant investment in your application. Now, just to reiterate, these VMs might be preempted at any time, and there's no charge if that happens within the first minute. Also, preemptible VMs are only going to live for up to 24 hours, and you only get a 30-second notification before the machine is preempted.
It's also worth noting that there are no live migrations nor automatic restarts in preemptible VMs. But something that we might want to highlight is that you can actually create monitoring and load balancers that can start up new preemptible VMs in case of a failure. In other words, there are external ways to keep restarting preemptible VMs if you need to. One major use case for preemptible VMs is running batch processing jobs. If some of those instances terminate during processing, the job slows, but it does not completely stop. Therefore, preemptible instances complete your batch processing tasks without placing additional workload on your existing instances, and without requiring you to pay full price for additional normal instances.
Spot VMs are the latest version of preemptible VMs. Spot VMs are virtual machine instances with the spot provisioning model. New and existing preemptible VMs continue to be supported, and preemptible VMs use the same pricing model as spot VMs. However, spot VMs provide new features that preemptible VMs do not support. For example, preemptible VMs can only run for up to 24 hours at a time, but spot VMs do not have a maximum runtime. Like preemptible VMs, Compute Engine might preempt spot VMs if it needs to reclaim those resources for other tasks. The probability that Compute Engine stops spot VMs for a system event is generally low, but might vary from day to day and from zone to zone depending on current conditions. Spot VMs are finite Compute Engine resources, so they might not always be available. Like preemptible VMs, it's worth noting that spot VMs can't live migrate to become standard VMs while they are running or be set to automatically restart when there is a maintenance event. There are many best practices which can help you get the most of using spot VMs. For example, resources for spot VMs come out of access and backup Google Cloud capacity. Capacity for spot VMs is often easier to get for smaller machine types, meaning machine types with less resources like vCPU and memory.
If you have workloads that require physical isolation from other workloads or virtual machines in order to meet compliance requirements, you want to consider sole tenant nodes. A sole tenant node is a physical Compute Engine server that is dedicated to hosting VM instances only for your specific project. Use sole tenant nodes to keep your instances physically separated from instances in other projects, or to group your instances together on the same host hardware. For example, if you have a payment processing workload that needs to be isolated to meet compliance requirements. The diagram on the left shows a normal host with multiple VM instances from multiple customers. A sole tenant node is shown on the right, and it also has multiple VM instances, but they all belong to the same project. You can also fill the node with multiple smaller VM instances of varying sizes, including custom machine types and instances with extended memory. Also, if you have existing operating system licenses, you can bring them to Compute Engine using sole tenant nodes, while minimizing the physical core usage with the in-place restart feature. To learn how to create nodes and place your instances on those nodes, see the link section of this video. Another compute option is to create a shielded VM. Shielded VMs offer verifiable integrity to your VM instances, so you can be confident that your instances haven't been compromised by boot or kernel-level malware or rootkits. Shielded VMs is the first offering in the Shielded Cloud Initiative. The Shielded Cloud Initiative is meant to provide an even more secure foundation for all of Google Cloud by providing verifiable integrity and offering features like VTPM shielding or sealing that help prevent data exfiltration. In order to use these shielded VM features, you need to select a shielded image. We'll learn more about images in the next section. Confidential VMs are breakthrough technology that allows you to encrypt data in use while it's been processed. Google Cloud's approach to encrypt data in use is simple, easy-to-use deployment without making any code changes to their applications or having to compromise performance. You can collaborate with anyone, all while preserving the confidentiality of your data. A confidential virtual machine, or confidential VM, is a type of N2D Compute Engine VM instance, running on hosts based on the second generation of AMD EPYC processors, codenamed Rome. Using AMD Secure Encrypted Virtualization, or SEV, confidential VM features built-in optimization of both performance and security for enterprise-class high-memory workloads, as well as inline memory encryption that doesn't introduce significant performance penalties on those workloads. The AMD Rome processor family is specifically optimized for compute-heavy workloads, with high memory capacity, high throughput, and support for parallel workloads. In addition, AMD SEV provides for confidential computing support. With the confidential execution environments provided by Confidential VM and AMD SEV, Google Cloud keeps customer-sensitive code and other data encrypted in memory during processing. Google does not have access to the encryption keys. You can select the confidential VM service when creating a new VM using the Google Cloud Console, the Compute Engine API, or the G-Cloud command line tool.
Okay, so these are a lot of details. Interesting, of course.
Next, let's focus on images. When creating a virtual machine, you can choose the boot disk image. This image includes the bootloader, the operating system, the file system structure, any pre-configured software, and any other customizations. You can select either a public or custom image. As you saw in the previous lab, you can choose from both Linux and Windows images. Some of these images are premium images, as indicated in parentheses with a P. These images will have per second charges after a 1 minute minimum, with the exception of SQL Server images, which are charged per minute after a 10-minute minimum. Premium images vary with the machine type. However, these prices are global and do not vary by region or zone. You can also use custom images. For example, you can create and use a custom image by pre-installing software that's been authorized for your particular organization. You also have the option of importing images from your own premises or workstation or from another cloud provider. This is a no-cost service that is as simple as installing an agent, and I highly recommend that you look at it. A machine image is a compute engine resource that stores all the configuration, metadata, permissions, and data from one or more disks required to create a virtual machine instance. You can use a machine image in many system maintenance scenarios, such as creation, backup and recovery, and instance cloning. Machine images are the most ideal resources for disk backups, as well as instance cloning and replication.
Cancel.
Images are the most ideal resources for disk backups.
Okay, so we have a machine image, persistent disk snapshot, custom image, instance template. Instance template is just configuration of the machine. Machine image saves.
Highly recommend that you look at it. A machine image is a compute engine resource that stores all the configuration, metadata, permissions,
Data from one or more disks required to create
and data from one or more disks required to create a virtual machine instance. You can use a machine image.
So base image replication, instance cloning, differential backup, multiple disk backup, single disk backup. So persistent disk snapshot is just single disk backup and differential backup. I cannot clone the VM. Okay, persistent disk backup, snapshot. Okay, because we're just saving the data here. Instead, we're saving also the information about the machine. Okay. Then custom image will not have information. Well, multiple disk backup. Okay. So it's necessary to have metadata in order to be able to make differential backup and also multiple disk backup, different metadata actually.
In many ideal resources for disk backups, as well as instance cloning and replication.
Okay.
At this point, you've chosen an operating system, but that operating system is going to be included as part of some kind of disk. So let's look at the disk options. Every single VM comes with a single root persistent disk, because you're choosing a base image to have it loaded on. This image is bootable in that it can attach to a VM and boot from it. And it is durable in that it can survive if the VM terminates. To have a boot disk survive a VM deletion, you need to disable the delete boot disk when instance is deleted option in the instance properties. As we discussed earlier, there are different types of disks, so let's explore these in more detail.
The first disk that we create is what we call a persistent disk. That means it's going to be attached to the VM through the network interface. Even though it's persistent, it's not physically attached to the machine. This separation of disk and compute allows the disk to survive if the VM terminates. You can also perform snapshots of these disks, which are incremental backups that we'll discuss later. The choice between HDD and SSD disks comes down to cost and performance. To learn more about disk performance and how it scales with disk size, refer to the link in the course resources for this module. Another cool feature of persistent disk is that you can dynamically resize them even while they are running and attached to a VM. You can also attach a disk in read-only mode to multiple VMs. This allows you to share static data.
So network storage appearing as a block device. Okay, so persistent disk is not something really attached to the machine, also because we don't really have a machine. And attached to a VM through the network interface, durable storage, can survive VM terminate, bootable, you can attach to a VM to boot from it, snapshots, incremental backup, scales with size.
Between multiple instances, which is cheaper than replicating your data to unique disk for individual instances. Zonal persistent disks offer efficient, reliable block storage. Regional persistent disks provide active disk replication across two zones in the same region. Regional persistent disks deliver durable storage that is synchronously replicated across zones and are a great option for high-performance databases and enterprise applications that also require high availability. When you configure a zonal or regional persistent disk, you can select one of the following options. Standard persistent disks are backed by standard hard disk drives and are suitable for large data processing workloads that primarily use sequential IOs. Performance SSD persistent disks are backed by solid-state drives and are suitable for enterprise applications and high-performance databases that require lower latency and more IOPS than standard persistent disks provide. Balanced persistent disks are also backed by solid-state drives. They are an alternative to SSD persistent disks that balance performance and cost. These disks have maximum IOPS as SSD persistent disks and lower IOPS per gigabyte. For most VM shapes, except very large ones, these disk types offer performance levels suitable for more general-purpose applications at a price standpoint between that of standard and performance persistent disks. Extreme persistent disks are zonal persistent disks also backed by solid-state drives. Extreme persistent disks are designed for high-end database workloads, providing consistently high performance for both random access workloads and bulk throughput. Unlike other disk types, you can provision your desired IOPS. By default, Compute Engine encrypts all data at rest. Google Cloud handles and manages this encryption for you without any additional actions on your part. However, If you want to control and manage this encryption yourself, you can either use Cloud Key Management Service to create and manage key encryption keys, which is known as customer managed encryption keys, or create and manage your own key encryption keys, known as customer supplied encryption keys. Now, local SSDs are different from persistent disks in that they are physically attached to the virtual machine. Therefore, these disks are ephemeral but provide very high IOPS. For up-to-date numbers, I recommend referring to the documentation in the course resources for this module. Currently, local SSDs are 375 gigabytes in size, and you can attach up to 24 SSD partitions for a total of 9 terabytes per instance. Data on these disks will survive a reset, but not a VM stop or terminate, because these disks can't be reattached to a different VM.
You also have the option of using RAM disks. You can simply use TMPFS if you want to store data in memory. This will be the fastest type of performance available if you need small data structures. I recommend a high memory virtual machine if you need to take advantage of such features, along with a persistent disk to back up the RAM data. In summary, you have several different disk options. Persistent disks can be rebooted and snapshotted, but local SSDs and RAM disks are ephemeral. I recommend choosing a persistent HDD disk if you don't need the performance, but just the capacity. If you have high performance needs, start looking at SSD options. Persistent disks offer data redundancy because the data on each persistent disk is distributed across several physical disks. Local SSDs provide even higher performance, but without data redundancy. Finally, RAM disks are very volatile, but they provide the highest performance. Now, just as there's a limit to how many local SSDs you can attach to a VM, there's also a limit on how many persistent disks you can attach to a VM. As illustrated in this table, this limit depends on the machine type. For shared core machine type, you can attach up to 16 disks. For the standard, high memory, high CPU, memory optimized, and compute optimized machine types, you can attach up to 128 disks. So you can create massive amounts of capacity for a single host. Now remember that little nuance when I told you about how throughput is limited by the number of cores that you have. That throughput also shares the same bandwidth as disk I/O. So if you're planning on having a large amount of disk I/O throughput, it will also compete with any network egress or ingress throughput. So remember that, especially if you'll be increasing the number of drives attached to a virtual machine. There are many differences between a physical hard disk in a computer and a persistent disk, which is essentially a virtual network device. First of all, if you remember, with normal computer hardware disks, you have to partition them. Essentially, you have a drive, and you're carving up a section for the operating system to get its own capacity. If you want to grow it, you have to repartition. And if you want to make changes, you might even have to reformat. If you want redundancy, you might have to create a redundant disk array. And if you want encryption, you'll need to encrypt the files before writing them to a disk. With cloud persistent disks, things are very different, because all that management is handled for you on the back end. You can simply grow disks and resize the file system because disks are virtual network devices. Redundancy and snapshot services are built in, and disks are automatically encrypted. You can even use your own keys, and that will ensure that no party can get to the data except you, because all that management is handled for you on the back end.
Okay.
You can simply grow disks
Computer persistent, cloud persistent disks. Okay.
and resize the file system because disks are virtual network.
Now that we have covered all the different compute, image, and disk options, let's look at some common actions that you can perform with Compute Engine. Every VM instance stores its metadata on a metadata server. The metadata server is particularly useful in combination with startup and shutdown scripts because you can use the metadata server to programmatically get unique information about an instance without additional authorization. For example, you can write a startup script that gets the metadata key value pair for an instance's external IP address and use that IP address in your script to set up a database. Because the default metadata keys are the same on every instance, you can reuse your script without having to update it for each instance. This helps you create less brittle code for your applications. Storing and retrieving instance metadata is a very common Compute Engine action. I recommend storing these startup and shutdown scripts in cloud storage, as you will explore in the upcoming lab of this module.
Another common action is to move an instance to a new zone. For example, you might do so for geographical reasons or because a zone has been deprecated. You can move a VM even if one of the following scenarios apply. The VM instance is in a terminated state, or the VM instance is a shielded VM that uses UEFI firmware. If you move your instance within the same region, you can automate the move by using the gcloud compute instances move command. To move your VM, you must shut down the VM, move it to its destination zone or region, and then restart it. After you move your VM, update any references that you have pointing to the original resource, such as any target VMs or target pools that point to the earlier VM. During the move, some server-generated properties of your VM and disks change. If you move your instance to a different region, you need to manually do so by following the process outlined here. This involves making a snapshot of all persistent disks and creating new disks in the destination zone from that snapshot. Next, you create the new VM in the destination zone and attach the new persistent disks, assign a static IP, and update any references to the VM. Finally, you delete the original VM, its disks, and the snapshot. Speaking of snapshots, let's take a closer look at these.
Snapshots have many use cases. For example, they can be used to back up critical data into a durable storage solution to meet application, availability, and recovery requirements. These snapshots are stored in cloud storage, which is covered later. Snapshots can also be used to migrate data between zones. I just discussed this when going over the manual process of moving an instance between two regions, but this can also be used to simply transfer data from one zone to another. For example, you might want to minimize latency by migrating data to a drive that can be locally attached in the zone where it is used. Which brings me to another snapshot use case of transferring data to a different disk type. For example, if you want to improve disk performance, you could use a snapshot to transfer data from a standard HDD persistent disk to a SSD persistent disk.
Now that we've covered some of the snapshot use cases, let's explore the concept of a disk snapshot. First of all, this slide is titled Persistent Disk Snapshots because snapshots are available only to persistent disks and not to local SSDs. Snapshots are different from public images and custom images, which are used primarily to create instances or configure instance templates, in that snapshots are useful for periodic backup of the data on your persistent disks. Snapshots are incremental and automatically compressed, so you can create regular snapshots on a persistent disk faster and at a much lower cost than if you regularly created a full image of the disk. You can create a snapshot schedule to regularly and automatically back up your zonal and regional persistent disks. As we saw with the previous examples, snapshots can be restored to a new persistent disk, allowing for a move to a new zone. To create a persistent disk snapshot, refer to the module PDF under Course Resources. Another common compute engine action is to resize your persistent disk. The added benefit of increasing storage capacity is to improve I/O performance. This can be achieved while the disk is attached to a running VM without having to create a snapshot. Now, while you can grow disks in size, you can never shrink them, so keep this in mind.
Let's get started with the second lab of this module. In this lab, you will be setting up an application server. Now, this example happens to be a gaming application, but it applies to many other use cases. You will configure the VM and also add capacity for a production gaming system, and you will build the infrastructure that you need for production activities. These include backups and graceful shutdown and restart services.
Let's go. So we have 7 tasks. We'll create a VM, prepare the data disk, install and run an application, allow client traffic, schedule regular backups, server maintenance, and review. Let's go. So we start now. I hope to finish it in half an hour. Okay. There we go. Therefore, task 1, create VM. We need a VM called like this, US Central 1A. So compute engine, VM instance, create instance. Oh, Jesus. This bug is something I hate. Sometimes the cloud. Oh my God. What the fuck? Oh, Jesus. Okay. So it was just a pop-up down here. Fuck them. US Central 1A. Okay. So the image we want is this one, and identity and API access, set access for each API. Storage, read, write. Read, write, okay. Now go to advanced option disk and backups, add new disk. Add new disk. Minecraft disk. SSD persistent. Oop. And it will be 50 gigas Google managed encryptions. Okay, specify the following and leave the remaining settings as their default. Network tags. Okay, let's see if we have something else here. Okay, so let's go to networking, network tags, Minecraft server. Network interfaces. Click default to edit the interface. Reserve static external IP address. So we need a static external IP address. Name, let's see, server IP. Okay, click reserve, done, create. Okay, so we basically configured this machine to have access to this API storage read write. Then for the networking, we attribute a type which we'll use for firewall rules probably. And then we added a new disk, just a SSD persistent disk. And then we also configured the default network to reserve a static IP address. And now we create it. Okay, prepare the data disk. The disk is attached to the instance, but it's not yet mounted and formatted. For MC server, click SSH. To create a directory that serves the mount point for the data disk, run the following command. So we first create a directory, and then we format the disk, and then we mount the disk. Okay. Let's go. So let's see. Here we go. You can see it. We are going to create this directory. And then we're going to format the disk. To format the disk, okay, so we identify the disk like this. These are the formatting options. Makefs is the command to Makefs is a command used to format a block storage device with a specific file system. Okay, so we'll format it as ext4, and then some other table adjustments, and then this is interesting, dev disk by the Google Minecraft disk. We call this disk Minecraft disk here. So let's go, we'll just execute this command. Discarding device blocks, file systems per block backup, allocating group tables done. Okay, looks like we have an output like this. Okay, now we're going to mount disk here. It's going to be mounted in this directory. Okay, check my progress. Great. Now install and run the application. So the Minecraft server runs on top of Java virtual machine, so it requires the to run because the server doesn't need a graphical user interface. Use the headless version of JRE. This reduces your resource, which helps ensure that the Minecraft server has enough room to expand its own resource uses. Okay. Sudo update on the sim server. Update the packages. Then we install the folder headless. Install headless because the server doesn't need a graphical user interface. And then we navigate to the disk basically. We install pget. So in the machine we installed the Java runtime environment. Now we have vget Minecraft server jar file. Okay. So we downloaded the jar file. Now we start the server without a GUI. Oh, look here. So fail to load properties, blah, 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 fail to load EULA, you need to agree to EULA. Microservice won't run unless you accept the terms of the end user license agreement. So to see the files that were created in the first initialization, we can just run an ls. You could edit the server properties files to be fair, we have a Minecraft server. Okay. So we just go to the EULA.txt. Of course, we change it to true. We save it, we exit. And don't try to restart Minecraft server yet, use a different technique in the next procedure. So create a virtual terminal screen to start the Minecraft server. So if you start Minecraft server again now, it's tied to the life of your SSH session. That is, if you close SSH terminal, the server is also terminated. To avoid this issue, you can use Screen, an application that allows you to create a virtual terminal that can be detached, becoming a background process, or reattached, becoming a foreground process. When a virtual terminal is detached to the background, it will run whether you are logged in or not. Okay, so let's install Screen. To start your Minecraft server in a Screen virtual terminal, run the following command. Okay, so the command is basically saying inside this virtual terminal, do the same we did before. Okay, now detach from the screen and close your SSH session. So to detach the screen terminal, press Ctrl-I, Ctrl-D. The terminal continues to run in the background. To reattach the terminal, return the following. Reattach the terminal. Ctrl-A, Ctrl-D. So to reattach it, okay. To exit it, run the following command. Allow client traffic. So create a firewall rule, go to VPC network firewall, create firewall rule. So the rule will be called Minecraft rule. Let's go to our VPC network. Create firewall rule named Minecraft rule. Target, specify target tags. Then target tags, Minecraft server. Source filter IPv4 all IPs. Then specified ports and protocols. Okay, and we select TCP, this one, 25.56.5. Click create. User can now access your server from their Minecraft clients. Create. Okay. verify server availability. Navigate to the PC network. In the left pane, click IP addresses. VPC. Okay, IP addresses. Locate and copy the external IP address for the MC server VM. It should be this one. Use Minecraft server status to test your Minecraft server. Wow. Perfect. So we now have a working Minecraft server. The web server working, okay. Use Minecraft server status, check my progress. Great. Now schedule regular backups. Create a cloud storage bucket. Cloud storage buckets. Oh, we'll do it from the VM instance with SSH. Okay. Sorry. So compute engine, VM instances. Let's open our SSH. Okay. Create a globally unique bucket name and store it in the environment variable your bucket name. To make it unique, you can use your project ID, run the following command. So, okay. Project ID, this. Okay, so verify it with echo. We should have it. Great. To create the bucket using the cloud storage tool, part of the cloud SDK, run the following command. Okay, so here we're going to store the Minecraft backup, Minecraft disk backup. Create, yes. Okay, so we created a bucket. If this command failed, you might not have created a new bucket name. Okay. To make this environment variable permanent, you can add it to the roots profile by running this command. I will not do it, but yeah, we've seen this in some videos before. So you basically write in this, yeah, you write in this file here the environment variable for this virtual machine, but yeah, I will not do it in this case. So let's go to our disk and let's create a backup script. Okay, so in the file we'll put this script here. We can measure it better here. So screen, save all, save off. Okay, so we reestablish, we reattach. Okay. We bring the process to the foreground, basically. Then we use this command here from user binary, okay, because we have the SDK installed, maybe. So we use this command to copy okay, this folder here from path, which is based on the system, and we'll copy that folder word, which I imagine is relevant for Minecraft. I'm not a Minecraft player. However, we'll copy it in our bucket under this Okay, so we'll create another bucket. No, it will be just a file in the bucket. Not sure. A folder in the bucket. Yeah, it will be a folder using also the date and then the suffix, the suffix word, and then we'll detach again the process. Okay, so let's save this. Let's exit. The script saves the current state of the server word data and pauses the server's autosave functionality. Next is it backs up the server word data directory and places its content in a timestamp directory in the cloud storage bucket. After the script finishes backup, it resumes autosaving on the Minecraft server. Save off, save on. Okay, so we'll not basically bring in forward and backward in the background the process. We're continuing to use the virtual terminal to send commands. Okay, so X stuff. Okay, so basically this shall be something related to Minecraft, but yeah, okay. So to make this script executable, we change chmod will be the chmod is changing is the command that calls to change the access permission. Okay, modality to access. Okay, I always forgot this. Test the backup script and schedule a cron job. Okay, so now we schedule a cron job. Okay, so now we executed basically. After scripts finish, return to the cloud console, click cloud storage buckets. Okay. So if we go to the buckets, I'm not sure if it worked as it didn't find the screen. What it looks like, yeah, it worked. Okay. So click on the backup bucket name. You should see a folder with date stamp. So open the cron table for editing. So now we'll change the frequency or what? Knock a cron tab for root using an empty one. Select an editor. Change later. Okay, so we'll choose nano. Okay, when you are prompted to select, yeah, at the bottom of the cron table, paste the following line. So, okay, this is a notation to indicate the frequency with which we want to execute the backup. It says every 4 hours. So, okay. Minute, hour, day, month, day of month, okay, and day of week. Perfect. Not the line instructs cron to run. Okay. Save. Exit. And then this creates about 300 buckets a month in cloud storage, so you will want to regularly delete them, which charges Cloud storage offers the object lifecycle management feature to set a time to live for objects. Okay. So server maintenance. To perform server maintenance, you need to shut down the server. So, okay, connect, and then we'll basically tell X stuff to stop. Okay, VM instance, select M server, stop. Okay, so exit because we're going to stop it. Where is stop? Wait, stop. Okay, we logged out of this. Oh, to start up your instance again, we visit the instance page and then click start. Can start with this time remote. You're pressing. I'm sorry, new server. Okay. Automate server maintenance. Instead of following the manual process to mount the persistent disk and launch the server application in a screen, you can use metadata scripts to create a startup script and shutdown script to do this for you. Okay, so click and okay. We're going to modify the metadata for this virtual machine. Edit. Okay, click add an item and specify the following: startup script URL. And for, oh, okay, sorry. So startup script URL. And shutdown script. So we'll reference to the key, find these values. Okay. Not, you'll have to click add item to a shutdown script when you start your instance. The startup script amounts to, okay, start, when you stop in the shutdown script, store, okay, click scripts in cloud storage, okay, click save. Okay, so you just give an URL to a script saved in cloud storage. I see. Okay, completed it. Now we have the review. Okay, and then the end of the lab. We did it in half an hour. Great. So now we can continue and we'll finish this course.
In this lab, you created a customized virtual machine instance by installing base software, which was a headless Java runtime environment, and application software, specifically a Minecraft game server. You customized the VM by preparing and attaching a high-speed SSD, and you reserved a static external IP address so that the address would remain consistent. Using that IP address, you then verified the availability of the gaming server online. Next, you set up a backup system to back up the server's data to a cloud storage bucket. And then you tested that backup system.
As this is just a resume of what we completed until now. Okay, which statement is true of persistent disks? Once created, a persistent disk cannot be resized. That's false. Persistent disks are physical hardware devices connected directly to VMs. That's false. They are encrypted by default. Okay, and this is also false. Which statement is true of virtual machine instance in Compute Engine? VM in Compute Engine always maps to a single hardware computer in a rack. In Compute Engine, a VM is a networked service that simulates the features of a computer. All Compute Engine VMs are single tenancy and do not share CPU. No. Compute Engine uses VMware to create now. What are sustained use discounts? Purchase commitments for specific resources you know will use. No, you receive by using preemptible VM instances. Automatic discounts that you get for running specific Compute Engine resources for a significant portion of the billing month. Submit. Great. Now we go to the module review.
In this module, we covered the different compute, image, and disk options within Compute Engine, along with some common actions. The two labs provided you with real-world applications of most of the topics covered in this course. Remember, there are many compute options to choose from. If a predefined machine type does not meet your needs, you can also customize your own VM, and you can even create a sole tenant node. You can also install different public and custom images on the boot disks of your instances, and you can attach more disks if needed. Thank you for taking the Essential Cloud Infrastructure Foundation course. I hope you have a better understanding of how to architect with Compute Engine, and I also hope that the demos and labs made you feel more comfortable with using the different GCP services that we covered. Next, I recommend enrolling in the Essential Cloud Infrastructure Core Services course of the Architecting with Google Compute Engine series. In that course, we start by talking about Cloud IAM, and you will administer identity and access management for resources. Next, we'll cover the different data storage services in GCP, and you will implement some of those services. Then, we'll go into resource management, where you will manage and examine billing data of GCP resources. Lastly, we'll talk about resource monitoring, and you will monitor
Okay, so let me download this. I saved all the PDFs for this course. Great, so now we have everything. Okay, I can continue. Course resources, so this is the whole course PDF. Yeah, let's go. Congratulations, you've passed Essential Cloud Google Cloud Infrastructure Foundation. I have a new badge, guys. Now, let's go. So very satisfied, yeah. Submit. Now that I've finished everything, I can go here to have a look. 24 hours remaining, and I'm out of the promotion for the next league. I will need like 400 points. So yeah, I would need 400 points, which means a lot. Let's go have a look here. So we just completed this course, and our next step will be completing this other course here. Yeah, so it was the one advised at the end of this course. Therefore, I think that for today, I will just stop with this video. I will see you in the next video where I will start the Essential Google Cloud Infrastructure Core Services. Thank you.